Hey everybody, in this recording we are going to do the sixth and final guided example in a set relating to the use of the double angle identities. That doesn't mean that these 6 examples are the only style of examples that really exist. I just tried to give you a sample of a little bit of everything. I think this is a pretty easy identity to verify. So I would recommend, if you have felt confident on the last 5 guided examples, to go ahead, pause the video right now and try it, because it really is only like 2 steps. If you need a little bit of advice, I will give you some right now. If you don't want the advice, press pause and go for it. If you want a little advice, I would use the left-hand side and change that until it matches the right-hand side. Personally, I feel that that might be easier for students. So press pause if you think that's enough advice. If you don't think that's enough advice and you want some more help, not only are you going to use the left-hand side, but when you have a sum or a difference, or many sums and differences, an expression separated by addition, subtraction, a bunch of different terms, and it's raised to a power, you have to remember that you can't just give that exponent to each piece inside. You must expand with multiplication. In the case that we have something squared, in this case we have 2 terms being squared, we can use FOIL, first, outer, inner, last. So we would write sin x plus cosine x times, both in parentheses, sin x plus cosine x, and use FOIL. That was quite a bit of advice. So press pause now if you think that's enough. If that's not enough advice for you still, you are going to want to flip back in your notes or pull from your memory the Pythagorean identities. And you also just want to pay really close attention to what is on the right-hand side of the equal sign. Where are you trying to go? There are so many different ways to write a trig expression, and that's why verifying them is pretty cool. If you had to write an equation for something, if you could write it in a simpler way, after you do all this work to derive and create this formula that will work, and it looks absolutely wild, and then you take this big gross thing and you can really simplify it to something much more clean, well, that would be great, right? So verifying is a very, very, very cool concept. I think it makes you much better at algebra in general. So if you are back here and ready to go, we are going to get started. So let's go. First thing I'm going to do is my right side is not going to change until I'm done. I'm just going to put a check mark and that'll be the end of it. So my right side will still say 1 plus sin 2x. I'm just going to try to map out in my head how many steps I'm going to take to show you the work. You may not use the same number of steps if you were presented with this on a test or a quiz or something like that, but I'm going to go above and beyond to ensure that nobody's confused. So 1, 2, 3, maybe 4. I don't want to stretch it out too much, but I think I could break it out into that many steps to make sure nobody is confused. So, like I said, when you have something like this squared, we are going to write that out twice, because when you square something, you multiply it by itself. You do not just be like, you get a square and you get a square and just call it a day. That would be silly. You would get sine, see, now I'm writing sine squared. Where's my whiteout? Not on my desk. Here we go. Eek. Sorry, so ugly. Plus cosine x. If you did do what I was just describing and squared that, you would get sine squared plus cosine squared. And hopefully you guys all realize that that would be a Pythagorean identity and equal some certain number. And that certainly wouldn't make this an identity. If the directions say verify the identity, well, that's the way of the problem telling you, hey, this is a fact. Now show me why. Okay? If the directions on this problem had said solve, that would mean that this is not an identity. Well, I guess it could be, but it's not always true. It's only true for certain x values. And our job when solving is to figure out which x values that's true for. If the directions said simplify, you probably wouldn't have an equal sign. You would probably just have something like this. And when you simplified it, you maybe would get something like this. Maybe that's more simple. It's up to the, context of what you're using this for. find, evaluate. If this said evaluate, okay, evaluate. I'm just looking at the words above my head, trying to think like directions, what would happen. If it said evaluate, because it's the last example, let's make sure we tie it all together, come full circle, unit circle, get it? If we had to evaluate, it would say evaluate blah, blah, blah. It would give you an expression for x equals pi over 4. Like, so what does this whole thing equal when all is said and done at the angle x equals pi over 4? So something like that. Or if it said find the value of x for which this is true, or find what this is equal to when x equals blank. Find is a little flexible. All right, anyhow, blabbing is over. FOIL, first, outer, inner, last, first times first, sine times sine. That is sine x. You could put it in parentheses squared. Nobody writes that. We put the square right there. The way you say this is sine squared x. Got it? All right. Then that's first times first. Outer, okay, is sine x times cosine x. Now, I'm going to write sine x cosine x. I hope you know that x times y times x, those are the same thing. It's called the commutative property, not commutative property. You're not doing like communion, like church. Cosine x, sine x, multiplying that. For the sake of seeing clearly that they are actually the same, I'm going to write sine in front again, only because I did that before. Normally, really, I would already write on this step 2 sine x cosine x because, I already combined it in my head, but not everyone will. And last times last, cosine x times cosine x will be cosine squared x. Now, to make sure that, sorry, I'm rattling this a bit, to make sure that everybody is really listening to the explanation and not just fast forwarding to the answer, I think it's important that you listen. To show that you are truly listening, you are going to put the letters F, O, I, and L underneath each appropriate expression to show me that you are listening and not just copying what you see on the screen. Thank you much. Next step, sine x, sine squared x, and cosine squared x. All right? These are going to be buddied up. When you are allowed to rearrange the order of addition and subtraction, if I just switch the order, say, of these two, that's still commutative property. Sometimes we think of them as being grouped together and we're like, oh, we have sine squared x and cosine squared x. We're going to associate those together. And we have sine x and cosine x. We're going to associate those together, like the product of those. So I'm kind of playing around a little bit with the associative property. I'm going to associate these two together. I'm going to associate these two together. I'm not going into too much detail, but just to kind of throw that word out there again, old word from your Algebra 1 days. So we got those two, plus, so I just relocated that. It's over here now, okay? And then these two cutie patooties, we're going to combine to sine x cosine x. Again, you need to know that this is multiplication between the sine and the cosine. This is multiplication between the 2 and the sine. This, you do not distribute the 2 times sine, 2 times cosine. We talked about in other examples and recently during class how distributive property only applies when a number is being multiplied by a quantity in which you have sums and differences. So don't call it distribution when it's just multiplication. Careful, careful, careful. This right over here has a certain value. This is an identity. Again, to show that you're listening, you're going to draw you're going to underline this, draw a little arrow, and you're going to label it with that identity name. The name of that identity, hopefully you know it, is the Pythagorean identity, capital P, person's name, YTHAGOREAN, identity. And you could capitalize identity, proper name, okay? So that Pythagorean identity states that sine squared theta plus cosine squared theta equals 1. So I'm going to put down a 1. So make sure you had labeled that so I know you are listening. Now, the other thing we want to acknowledge here, if that was an alpha and that was beta, or x and y, this doesn't equal 1. They both have to be the same thing, theta and theta, x and x, or it's not true. or not necessarily true. Now this right here, maybe you don't know what to do with this at first. Just take a step back, look at where we're trying to go. We already have the 1 and the 1. So we're in pretty good shape, right? 1 and the 1. This is the only thing we have left to do. And the name of the lesson that we're on, or the unit that we're on, is using the double angle identities. So I need to somehow show that this is equal to this. Well, yeah, that's the double angle identity. In the lesson introduction video, when we introduced double angle identities, the first one we wrote down was sin2x equals 2sin(x) cosine x. We also showed a derivation of this identity using what? So if you know what we used to verify what identity specifically we used to verify this, you're going to put that right here in the corner with a little star in front of it. You're going to write, we used blank to derive sin2x equals 2sin(x) cosine x. All right. And this way I know you were listening to this video. So that next step, I'm going ahead and I write that down. We are done. We have verified. We have shown our work. Winner, winner, chicken dinner. So I hope you found this doable. Verified. And if you feel confident, then you can do another example like this. Thumbs up. If you don't feel confident, thumbs down. And I have one for you to do on your own, and that will be the on your own example number 6. On your own, please verify the following. Cotangent theta plus tangent theta equals 2 cosecant 2 theta. If you want advice, just keep listening. I'll give you some pointers on this example. If not, hope you have a great day. But advice would be, I would change the left-hand side here. Personally, either is absolutely doable. I would change the left-hand side over here. I would change everything into, me personally, I would change everything into cosecants and secants with those bonus quotient identities I gave you back in lesson 13 when we did the fundamental identities, which were the reciprocal, quotient, and Pythagorean. Okay, so I would change that first. Then I would find a common denominator to bring it all together. Then I would kind of slowly go from there. All right, and keep in mind, we talked about in an earlier example, I think 5, that cosecant 2 theta is really the same as the 1 over sine 2 theta. So it's 1 over what we just saw, 2 sine theta cosine theta. So if you can get your way to there, that would be really helpful. So I would definitely bust out your fundamental identities. Have those nearby, handy in front of you if they're not in your brain. And hopefully this advice will help you out. Have an awesome day. Bye.